everyone, and welcome to episode 4 of Explaining Physics Concepts. We're still doing thermal physics, and in this we will be taking a look at ideal gases, thermal physics for ideal gases, and very important two derivations. And I will be explaining all of that in full detail, so let's begin without wasting any more time. So starting off with ideal gas, this is more of related to chemistry, I would say, but it's like you must have heard what is moles, right? So amount of substance. So whenever you have, so I'm going to start from the basics. So we have amount of substance is measured in moles, right? So moles are used to measure amount of substance. Now you must have seen this formula. If you want to find out number of particles or number of atoms or number of molecules, if you want to find these out, you denote them with capital N. You multiply number of moles, which you can write as N times Na. What is Na? Na is the Avogadro mass constant, which is 6.02 × 10⁻23. So this is a formula that you must have seen in your previous classes and in chemistry as well. If you want to find out amount of atoms or number of particles, number of atoms, you multiply number of molecules into this constant 6.02 Avogadro mass constant 6.02 into 10⁻23. This is how you find the number of particles. Now I would highlight this formula because, and you have to know these symbols as well, because we are going to do something very important related to this. Now next part is I'm going to see the relationship between pressure, which is P. I'll write pressure. Then we have volume. You must have done it as before as well, and then you have temperature, which is T. Now you obviously know when you increase the temperature, the particles, they gain more energy, and so they start colliding with each other with more force, with more pressure. So temperature and pressure, they are directly proportional. So I can say pressure is directly proportional to temperature. What about pressure and volume? Obviously, when pressure it decreases, okay, so volume is how much space it takes. Okay, so if you have this huge of a balloon, right? If you have a balloon like this, now if it has a lot of volume, so the particles have a lot of space, so they're not going to collide with each other as frequently as they would if the balloon is this small, and if let's say these are particles in this small, the particles are very close to each other, and so they are colliding with each other more frequently, and so they are exerting more pressure, more force. So the volume here is less, but pressure is more. Here volume is more, pressure is less. So volume and pressure, they are inversely. So I would say pressure is directly proportional to 1 over V. This is what it means, right? And in this case, also when you're comparing two things, when you're seeing their proportionality for three things, if you're seeing the proportionality between pressure and volume, the third thing always has to be a constant. I can only say that pressure is inversely proportional to volume when temperature is constant. This always has to remain constant, or if you're looking at volume and temperature, this always has to remain constant. One of the three things always has to remain constant while seeing the relationship between the two of the things. So I would say when pressure is directly inversely proportional to volume, temperature is constant. So the K is constant, right? And volume is directly proportional to temperature. When you increase the temperature, the particles start moving away because they start getting more energy, and so the volume increases. Now in this, when I'm looking at volume and temperature, I would say pressure is constant. This is how I would say. Now if I were to put them all, I can put them all in a good formulas as well, I would say. So okay, so if I were to convert this pressure and volume into equals to sign, this equals to sign, I always have to insert a constant, and that constant is T. So I would say pressure is equals to temperature over V. This is how I would write it. So one formula that I can say, if I were to make T the constant, I would say P1 V1 equals P2 V2. I can make one formula like this. And if I were to look at this one, V equals PT, because pressure is constant, because I removed this sign and got this. So if I were to make, okay, so essentially what I'm doing in this, the reason why I multiplied P with V and kept T the constant is because I'm having constant as the subject of my equation. In this, if I want to have the constant, the P, as the subject of the equation, I'll have V1 over T1 equals V2 over T2, and that is equals to the constant. This is one formula. It's the formula is usually used when you have to like see the difference between two things. And another is, we're done with PV, we're done with VT, we're left with P and T. Since P and T are directly proportional, so it will be P1 T1 equals P2 T2, because P over T equals volume, which is my constant. So this is another formula. If I were to show this to you in a graph form, obviously you know when things are proportional to each other, they go directly through the origin straight line, and that can be seen in volume and temperature, or that can be pressure and temperature as well. But when things are inversely proportional to each other, they always go like this. This is how you see a graph, and that can be seen at pressure and volume. Now that we're done with this, let's move on towards our next important thing, that is Boltzman constant. Now, if I were to take these, okay, so if I were to take one of these formulas, this one, P, V, okay. Now, what I would say, you must have seen this formula for ideal gas, PV equals nRT, right? This is a formula for ideal gas. Do you know how we derive this? So essentially, let me tell you where the R came from. That is, if we do Boltzmann constant, Boltzmann constant is defined as K, and it is equals to R over Na. I hope you always you remember that Na is equal to Avogadro constant. So K equals R Na. This is a formula that you need to learn. Boltzmann constant, that is K equals R Na. So N RT, let me tell you, this is the number of moles, R is this thing here, this is a constant as well. Now from this I will derive another formula. Let's go with this. Okay, we know PV equals nRT, right? Now, do you know what R is? This R is here. This R equals KNA. R equals KNA. So what I'll do is replace N K N A T. I get this. The reason why I'm doing all of this is we're just looking for another formula for PV. Since PV equals nRT, we're going to be taking a look at a similar formula. So all I have to do is, okay, I have R equals KNA. I replace that KNA. Now does this ring any bell, N and A. If we go back, N and A equals capital N. So this N and this NA, this equals to capital N, number of atoms, particles, molecules equal number of moles into Avogadro. So I can just replace this and I can have PV equals NKT, and this is another formula that you can learn. So all you have to do, you know PV equals nRT, and we know Boltzman constant. You just write another formula by replacing things and substituting and etc. Now we're going to move on towards the basic assumptions of kinetic theory of gases. I did mention it in our last video as well. How there are certain assumptions, kinetic theory of gas, that assumption that we make about them, right? About the ideal gas. So starting off with a first one. Number is the molecules are in. All of this is about ideal gas. The molecules are in constant, continuous random motion. The molecules are in continuous random motion. Number 2, all collisions are elastic. Number 3, there are no intermolecular forces of attraction. There are no intermolecular forces of attraction between molecules. Number, which are we? This is 1, this is 2, this is 3. The number of the volume of molecules. The volume of molecules is negligible compared with the volume of gas. So these are a few of the kinetic theory of gas assumptions that we make about ideal gases, and you can just learn them, you can understand them, and then you can see how there are no forces of attraction, they're in continuous random motion, and the volume of molecules is negligible compared to the volume of gas. Having done this, now we're going to move on towards the derivations, and I would say the most important derivations, and you have to be very important and stay with me throughout the derivation, because if you lose focus midway, you won't understand anything. Now, a first derivation is, again, we're just look at more formulas for PV equals nRT, PV equals NKT. Now we're going to take a look at another formula. Now for that, I'm going to draw a cube. And I'm going to assume the length of this cube is L, and there is a particle inside this cube, and it's moving in this direction with the speed of cx. Okay, we're just going to assume that. Now, starting off with the first step, do you know what momentum is? Momentum is P equals mass into speed, right? And speed is cx. I'll just say this is speed. Now, what is the total momentum change in momentum? That is going to be 2mcx. We do this when there's a rebound. So the particle, it goes here, it hits this wall, and then it rebounds. So this is 2mcx. Now, this is speed. Do you know what speed is? Speed is distance upon time. What's the distance that is traveling? L. since this is a cuboid, this is L, this is L, this is L as well. All of the sides are L. So L over T time, right? Now, since we're saying it's a rebound, since it's going to travel in this direction, capital L, and then it's going to travel in this direction, L, so it's going to become 2L. So time, if you make T the subject, it will be 2L over Cx. Okay, I hope this makes sense. And then do you know rate of change of momentum, F? That is rate of change of momentum over time. Force is rate of change of momentum over time. Now we know what this P is, change in P is, delta P is, that is 2m Cx over T. Now what is T? T is 2L divided by 2L over Cx, and since we have to do now reciprocal, so this becomes 2m Cx square over 2L. 2 cuts, you get mcx square over L. mcx square over L. Then comes the twist. Let me highlight this because this is important. mcx square over L. Now, what is, this is another part, so let me just do it with purple. Okay. What is pressure? Pressure equals force over area. We're just linking things now. What is force? Force is here, mcx square over L. Okay, mcx square over L. What is area? Area is L squared of the cube. Area of the cube, L square. This becomes mcx square over L cube. Now what's L cube? It's volume. So mcx square over volume. Now all of this is related to just one particle in this cube, right? But there will be thousands and many of these particles similar to this. So I'll denote them with N, because you remember we said capital N is number of atoms, number of particles. So N, M, and since we have to take the speed of all the particles, so we will be taking the average speed. So this symbol, this means average. So this is a symbol that means average. So Nm, average speed over V. Now another tip, 1/3 of c square equals cx square. This is something that you have to learn. Cx square is equals to 1/3 c square. So instead of this, I'll write 1/3 N c square over V. And what I'll do, since I have to get the formula for PV, PV equals 1/3 NmC square. So this c square, this is it means the square speed, means square speed. It means mean square speed. So we started off with, so let me explain. This is our final formula. Now if you look at the cube again, you'll see how we started off with just one formula. We looked at its speed, we looked at its distance and all of that, and we said, and then we just started broadening it that there will be many particles similar to this. So we started wanting to take mean speed of all of them, the average speed, average mean speed of all of them. That is why we have all of this, and n, and then because all of that. With that, I have another derivation. It's very similar to this. Again, second derivation. Again, we have to find, we will be using the same formula, the ones that we have. PV equals NKT, right? We derived this formula up. And then we have another formula, PV equals 1/3 Nm C square. Now let's just replace both of them. I have nkt equals 1 by 3 nm c square. I cut these n out and I have kt equals 1 by 3 mc square. Now we're going to take a look at 1 by 2 mc square 0. Kinetic energy equals 1 by 2 mv square. So I have 1 by 2 wait. Okay. Now this is similar to 1 by 2 mc square, right? 1 by 2 mv square, the kinetic energy formula. How do I make this 1 by 2 instead of 1 by 3? I multiply this with 3 by 2. If I'm introducing something on my own, I have to do it on both sides. So 3 by 2 kt equals, I cut this and I get 1 by 2 mc square. So it becomes similar to the kinetic energy. Because let me explain why we're doing this. And now when we get 3 by 2 kt 1 by 2 mc square, do you notice how this is equals to the kinetic energy? K is a constant, 3 by 2 is a constant, so what we're actually narrowing it down to is that this temperature is directly proportional to Ek. So this is for like one molecule, right? So we are saying this is the average translational kinetic energy of one molecule. So what we do, we take this formula, we take that formula PV equals nRT, PV equals nKT, and then PV equals 1 by 3 nmc square. We put them together. We want to see the average translational kinetic energy, and we have to make it similar to 1 by 2 mc square. I introduce 3 by 2 to make it 1 by 2. I do the same on the left side here as well. I get 3 by 2 kt, since K is a constant, Boltzman constant, 3 by 2 is a constant, 1 by 2 is a constant. All of this is kinetic energy, so T is directly proportional to kinetic energy. That this temperature is directly proportional to the kinetic energy of one molecule. That is all. This is the reason why we did this, is to show you that the kinetic energy of a molecule only depends upon temperature. This was the reason of this. Now a very small quick thing before we end this part is, if you have c square, right, we talked about this is the average mean speed, right, is the mean square speed. If we take its square root, we get CRMS. What this is root mean square speed. We talked about this, we know what this is. If we take a square root, so obviously it becomes root mean square. If this was only mean square speed, this becomes root mean square speed. So if you get to this formula 3 by 2, if you use this formula 3 by 2 kt equals 1 by 2 m c square, And since these two, all of these are constants, right? I want to remove this equals to sign. I will cut all of these constants and I'll have this. And then what I do is, all I say is that CRMS. So we just want you to see the relationship between CRMS and temperatures. This is what it is. So we know how temperature is directly proportional to the kinetic energy, average translational kinetic energy of one molecule. That is the formula we made you to find the average translational kinetic energy of one molecule. And then we just wanted to see how this alone is mean square speed. If we take its square root, it becomes root mean square speed. And then I wanted to remove this, so I removed all of the constants and then take c square, and then I get CRMS. And this is it for this video. In our next video, we will be looking at thermodynamics and a past paper question, and all of the confusions you may possibly have, that they will be solved through these questions. But you can still drop them down in comments, and please do not forget to subscribe and like. Thank you.